Hello and welcome to our last lecture for ECE 108 this weekend on account of Canada Day. So in this lecture, we're going to talk all about those binomial coefficients we introduced in the last lecture, some of their properties, and some interesting fun facts. So here we have 15 slides to go through, but a lot of those are doing a proof, and that proof I'm actually going to do in Paint so you can see everything all at once. So we're not really going to cover 15 slides, so don't worry there. Okay, so the first thing we're going to talk about is Pascal's identity, or PI. So for all positive integers n and m, with m less than n, we have that this equality holds here. So this identity is very useful in practice because it gives us a recurrence relation that we can use to compute n choose m. So using that recurrence relation allows us to avoid computing n factorial from really, really large n, which, as I've mentioned before, can lead to issues if you're using doubles to store your data. I mean, it also gets into issues if you use ints or even unsigned ints, just because of the limitations there. So you'd really want to use arbitrary precision variables and computing n factorial for large n, but I digress. So the natural question we can ask is, how do you prove this? Well, the answer is you do a bunch of algebra, but that algebra that we're doing isn't trivial, just plug and chug type thing. There's a little bit of thought that goes behind it. So let's look at the proof real quick. Well, let m and m be positive integers with m is less than n. Then this term here plus this term here, what would that be equal to? Well, I can use the definition of n choose m to expand these out in terms of factorials. So let's do that. This is what this would be, so let's just go through and check to make sure this is right. So here I'd have n minus 1 quantity factorial on the top, which I have here. I would have this minus this quantity factorial, so n minus 1 minus m minus 1 quantity factorial, check. And I would have that multiplied by m minus 1 factorial here, check. So next I would have n minus 1 factorial, check. N minus 1 minus m factorial, check, and m factorial, check. So now that I have these two fractions, what do I do? Well, ultimately, n choose m is a single fraction, so I want to combine these to be one single fraction. So how can I do that? Well, the general trick is to find a common denominator. Well, before I actually find the common denominator itself, I can note this can be simplified. So I can simplify this by simply noting n minus 1 minus m minus 1. Well, the negative minus 1 cancel. So this term here will simplify to n minus m factorial, and that's what I did from this line to this line. So now let's find a common denominator. Well, m factorial is bigger than m minus 1 factorial. In particular, I need to multiply this by m to get m factorial. So here I want to multiply this fraction by m divided by m. And next, I note m minus 1 factorial is bigger than n minus m minus 1 factorial. And to convert this over to a n minus m factorial, I'd want to multiply this fraction by n minus m. So if I do that, this is what I get. So here, multiplying this by m gives me m divided by m factorial. Again, m times m minus 1 factorial by definition is m factorial. And for this fraction, when I multiply by n minus m on the top and the bottom, here I get a n minus m, and in the bottom, this multiplied by n minus m gives me n minus m factorial. So now I can add these two fractions. So adding them gives me this. Now, since this is not a live lecture, instead of using the next slides and kind of breaking this proof into 2 bits, I'm simply going to copy and paste from the other slides and do this all in Mr. Paint so that you have one continuous proof here. I think it's a bit cleaner that way. Okay, so here's what I had on the previous slide, and now I have these two fractions and I added them together to get a single fraction. Can I simplify this further? Well, this has an n minus 1 factorial in it, and this has an n minus 1 factorial in it, so I can factor out that n minus 1 factorial and rewrite this as n minus 1 factorial times m, the term here, plus the term in parentheses here. So I can simplify this as follows. Now from here, this term here that I just highlighted, This can be directly simplified to n, so I can write that this is equal to this expression here, where all I did between these two steps here is simplified this to be simply n. Next, I can note this whole thing here, just by definition, is n factorial. So this whole expression simplifies to simply be n factorial divided by n minus m factorial times m factorial. And by definition, this is the definition of n choose m. So I am now done with the proof. So if you kind of look at this given as a proof, you could get confused as why am I doing these various steps here? But to kind of see the forest through the trees for a second, what we're really doing is we had two terms here that can be written as two fractions, and we want one fraction on the other side. So I take my two fractions, I add them together to get a single fraction, and then I do some algebraic manipulation to try to turn that single fraction into something of this form here. So that's explicitly what I'm doing, and that's what I do on this slide here. Okay, so this recurrence relation, as I said before, gives me a way to compute n choose m using the, quote, previous binomial coefficients. By previous here, I mean I'm using n minus 1, so it's previous in that sense. So how would I build an algorithm to do this? Well, first, if n is equal to 0 and m is equal to 0, so let's draw that in, then n choose m would simply be 1. So this would be kind of my base case for this algorithm. And next, if I consider what n equals 1 looks like, I have two cases. Over here, I have my m is equal to 0, so my first line. And over here, I have my m is equal to 1, so my second line. So here, if I were to use my recurrence relation, I would have that 1 choose 0 would be equal to what? Well, for the first term, I'd have 0 choose negative 1. And for my second term, I would have 0 choose 0. So by the definition of choose, 0 choose negative 1, this is just 0. So if you wish, you could draw a little arrow over here with kind of a 0 to fill out this triangle. Generally, we ignore the zeros. And for this other term, it's simply this coefficient here. So when I compute this one, I'm taking 0 from over here plus 1 to get 1. And when I compute this one, I'm computing 1 plus a 0 to get the 1. So let's clean that out for now. So let's look at the next row. So to build the next row, what do? Well, to build this, I take 0 plus 1 to get 1. Here, I take 1 plus 1 to get 2. So I'm using these two other previous guys here. And this 1 is found by 1 plus 0 to get 1. And I can continue this forever, right? The next row, this will be a 1 because it's 1 plus 0. This term here is 1 plus 2. This, which is 3. This term here is 2 plus 1, which is 3. This is 1 plus 0, and so on. So this triangle is known as Pascal's triangle. It can be very useful for computing these combinations, and it can be also useful for other things, such as multiplying out a binomial expression. More on that in a second. But in general, this is just a handy way of computing these expressions here, and it's the way that you'd really compute them if you use this recurrence relationship here. So binomial theorem. Why did I refer to combinations as binomial coefficients? Well, we have a theorem. For all integers n greater than or equal to 0 and all real numbers x, this expression here is equal to this expression here. So explicitly, if I want to compute 1 plus x to the n, I simply compute these binomial coefficients and then build this sum. So one difference to note between my version of the binomial theorem and the version in your text, the version in your text uses what I would call the binomial theorem version 2, and the version in your text starts at n is equal to 1, but the theorem does work for n is equal to 0, so I'm starting from 0. Okay, so an example. Use Pascal's triangle to find x plus 1 quantity to the 5th. Well, the fifth row of Pascal's triangle can be computed pretty trivially. If I go back over here, this was the fourth row. So the fifth row would be 1. 1 plus 4 is a 5. Let's write this out. 1, I would have a 5 here. 4 plus 6 is a 10. 6 plus 4 is a 10. 4 plus 1 is a 5. And 1, I'd get a 1 here. So from this, I would know that the fifth row of Pascal's triangle is simply what I wrote out there. Therefore, if I wanted to write this out, the sum would simply be x to the fifth. So here, if I start at n and kind of count down, I would have my x to the n times 1 would be the first coefficient, so x to the fifth. The next bit would be 5, that would be the binomial coefficient here, times x to the fourth. The next bit would be 10, this binomial coefficient here, times x to the third, 10x squared, 5x plus 1. Again, you could do this the other way, but we usually write polynomials starting with the highest power. So yeah, so you can see how Pascal's triangle can be pretty powerful, and you can see why we would call these binomial coefficients, because they're the coefficients in this polynomial when I expand this binomial here. Okay, so in what follows in the next few slides, we are going to prove this theorem by using induction. So essentially, this proof is the same proof that's in your textbook, just with a few slight differences because I'm using a different polynomial here. Okay, so let's get at it. So we're going to use induction on n, where p sub n is the statement for all x in R. This term here is equal to this binomial expansion. So base case, what would the base case be? Well, in your book, they started with natural numbers, so the base case was 1. Here, since I'm starting at 0, the base case will be p of 0. So in p of 0, that's the statement for all x in R. X plus 1 to the 0 is equal to this sum. Well, is this true? Well, let's just examine the left-hand side and the right-hand side. Well, x plus 1 to the 0 is equal to 1, because anything to the 0 is 1. If you want to be really cautious here, you could say, what if x is equal to minus 1? Then I have 0 to the 0. Is that still 1? Well, yes, within this context. And then on the other side, I have the sum from m is equal to 0 to 0 of this thing. Well, what is this equal to? Well, the sum is simply 0 choose 0 times x to the 0, and all of this, again, will be 1. You could say, hey, what if x is 0? And again, it works in that case. So from here, since 1 is equal to 1, p of 0 is true, and the base case holds. So really, your book starts at n is equal to 1 to try to avoid this issue with 0 to the 0. So if you don't feel comfortable with making this argument here, that this thing is always equal to 1, you can throw away n and not have to deal with the gritty details. But here it really doesn't matter, so let's go on. Inductive step. So now we're going to let k be an arbitrary integer where k is greater than or equal to 0, and we're going to assume the inductive hypothesis p sub k. That is, we are going to assume that for all x in the real numbers, 1 plus x quantity to the k is equal to this expression here. So now I need to show that p sub k plus 1 is true. So what is p sub k plus 1? Well, it's this boxed expression here. This is what I want to prove. Well, I'm starting with this expression here, so how can I turn this left-hand side here into this left-hand side here? Well, explicitly, I can note 1 plus x to the k plus 1 is simply 1 plus x times 1 plus x to the k. And now here, I know that 1 plus x to the k is equal to the sum, so I can use my inductive hypothesis here to replace this term here with this finite sum. So now what do I want to do? I ultimately want to show that this highlighted expression can be written in this form here. Well, that looks like it could maybe be hard to do, and it actually isn't. So let's kind of look at how to do it using Paint rather than using the slides. Okay, so this was the starting point that I had from the slides. Now what do I want to do? Well, I have this sum, this finite sum times this expression here, and what I can simply do is pull this inside the sum and expand it out. So doing that, what do I get? Well, explicitly, I'll get this statement here. So what went on? Well, 1 times this sum will simply be the sum itself, and x times the sum, since it's a finite sum, I can pull the x on the inside, and I simply get x to the m plus 1 here. So now I ultimately need to rewrite this expression again as this expression over here. So how can I do that? Well, I need to somehow change this k to a k plus 1, and I need to somehow combine these two sums together to get this expression over here. Well, I have two binomial terms here, and do I have any theorems for how to combine the sum of two binomial coefficients? Well, I have Pascal's identity, right? So the basic idea is I'm going to algebraically rearrange these two sums to give me something for a coefficient that I can use Pascal's identity to get this term here. So how can I go about doing that? Well, if I go back to Pascal's identity, here I want to have one of these terms to have an m minus 1 and the other term to have an m. So here these were the same counter, so somehow I want to change one of these to m minus 1. And secondly, this is an m plus 1, but this is simply just an m. So I ultimately want these powers to be the same so I can add them, so I can combine these sums into 1. So one way I can go about doing both of these at one time is to simply do this change here. So I'm leaving the first sum alone and I'm modifying the second sum. How am I modifying it? Well, I'm doing a substitution. So here I initially started at m is equal to 0, and now I'm starting at I is equal to 1. And in order to keep everything the same here, I simply replace this m with an I minus 1 and this m with an I minus 1. So if you want to be explicit, what I'm really doing here is I'm saying let m equal I minus 1. And then from here, I'm doing the substitution at these two places, and I'm doing the substitution here. And 0 is equal to I minus 1 is the same thing as I is starting at 0. So that's what's happening here. And again, the reason why I'm doing this is so that now these two terms here in the sum, the powers look the same, and I now have an m and an I minus 1, which I is a dummy variable, so I could change it to an m if I wished, but that's kind of starting to look of the form of something that looks like this. It's not fully there yet, I need to do some details, but I'm starting to get there. So this isn't quite what I wanted yet, it's not of this form, it's still two sums that now kind of have this weird index thing going on. So if I wanted to combine these two sums into one solid sum, I have to have the indexes starting at the same points and ending at the same points, and ultimately using the same variable, but I can swap out I for m and not change anything there. So how can I make these indices both start and end at the same value? Well, here this sum starts at 0, whereas this sum starts at 1. So if I pop out the first term in this expression and pull it off to the front, then this sum would now start at 1. So by popping that out, I explicitly mean if I take m is equal to 1, so k choose 0, x to the 0, and pull that out, I would get this. And then I would have, just temporarily writing it in, plus this sum here, but instead of starting at 0, I will start at 1. So instead of this being a 0, I start here at a 1. So that's how I could pop this expression out. And further, the next problem I have is that this is a k plus 1, but this sum here ends at a k. So I can do a similar thing by popping off the k plus 1 term. And if I do that, what would this look like? Well, here I would have plus this sum starting from I is equal to 1, going up to k of this term here. And since I popped out my k plus 1 term, I would have plus one extra term that would explicitly be this expression here. So when I plug k plus 1 into here for I simply get k. So here I could do this expansion like this. And now I can note that these two sums here in this bit here now have the same indices, so I can just simply combine them together. So here I should be a bit careful. This is an m. So this is what is happening in those two steps on slide 8, where I go from this statement here down to this statement here. I'm doing this stuff in the middle. These all get combined. So here I have this first term plus the sum from m is equal to 1 to k. Again, it doesn't matter what I use as a dummy variable, of this term here plus this term here, and then finally plus this last term over here. So now what do I have? I have this expression here, and I want to show that this term that I've been considering down there can be written as this sum. So again, I still have a problem. This k should be a k plus 1. This k here should be a k plus 1. These two terms here should simplify to be the sum from m is equal to 1 to k of k plus 1 choose m x to the m. So I have a few terms here that are off and they're not explicitly what I want them to be. So how can I address this? Well, first I can notice over on the side that n choose 0 is equal to 1 for all non-negative integers n, right? Thus, I can change this k choose 0 to a k plus 1 choose 0 without changing its value. So doing that gives that this first term is equal to k plus 1 choose 0 x to the 0. Next, I can note k choose k. Well, how could I change that to k plus 1 choose k plus 1? Because that's the term I need over here. Well, n choose n was also equal to 1 for all non-negative integers n. So here I can change this k choose k to k plus 1 choose k plus 1 trivially. So here, this last expression can be written out like that. Okay, so those example combinations that I had previously were presented for a reason. And this middle term, what can I do with it? Well, it's simply going to be equal to this expression here, right? I can simply take this x to the m and factor it outside of the sum of the combinations. So how can I combine this to look like k plus 1 choose m? Well, we had our friend Pascal's identity, right? Pascal's identity was this expression here, so let me just copy it so we have it on the same slide. This is what Pascal's identity said, and now I can see that if I were to replace n minus 1 with k, then I can combine these two binomial terms using Pascal's identity. So by using Pascal's identity, this total sum here simply becomes this expression right here. So here, plugging these in and changing the variable, I simply get k plus 1 choose m as this expression here. And now finally, this term is the 0th term of this summand, and this term is the k plus 1 term of this summand. So I can combine these together and say the sum from m is equal to 0 to k plus 1 of this thing is equal to this expression. Now that's exactly what I wanted to show up here, so I am done. So let's go back to the slides. That's explicitly what I do in the rest of these slides here. So there's a little bit of carryover to put it into slide form, but yeah. So from there, thus p sub k plus 1 is true, and hence by the principle of mathematical induction, p sub n is true for all n greater than or equal to 0. So yeah, now let's look at a corollary, Binomial Theorem version 2. So this is the version that's in your book, again with the caveat that I'm starting at 0 instead of 1. So for all real numbers a and b, a plus b to the n is equal to this expression here. So note the only thing that really changed between Binomial Theorem version 1 and Binomial Theorem version 2 is that before I had a is equal to 1 and b is equal to x, and now I have a and b where these are arbitrary real numbers. So we're going to prove this using cases. We've already done the hard part of the proof in proving Binomial Theorem version 1. We no longer need to do induction here. So in case 1, if a is equal to 0, then we have that this sum is explicitly equal to this sum where I plug in 0 for a. And this term will be 0 for all of the values except for when n minus m is equal to 0. And in that case, I'll plug n in for m, and I get n choose n, b to the n, which is simply equal to b to the n. So that's simplifying the sum here. And on the other side, if I plug a is equal to 0 into this, a plus b to the n is 0 plus b to the n, which is just b to the n. So b to the n is equal to b to the n, and it holds for this case. Okay, so next, if my first case was a is equal to 0, and I'm only considering two cases, what would my second case be? Well, a is not 0. So if a is not equal to 0, what can I do? Well, if a is not equal to 0, if a is not 0, then I can take this whole expression here and I can rearrange it. So here I could say this is equal to a times 1 plus b divided by a, parentheses all around that, to the n. So here I can do this since a is non-zero, and I can just factor it out. From here, I could rewrite this further by saying this is a to the n times 1 plus b divided by a to the n. So now, since a is not equal to 0, a divided by b is going to be a real number, and Binomial Theorem 1 applies, where x is now just going to be b divided by a. So using Binomial Theorem 1, I can rewrite this sum as the a to the n stays out front. This will be the sum from m is equal to 0 to n of n choose m, b minus a to the m. So now from here, I can notice that this term can be simplified by writing it as a to the minus m times b to the m. Next, I can pull this a to the n inside the sum, and I can add the exponents. So here I'd have a to the n minus m times b to the m, and that's exactly what I wanted to show. So here, since the results hold for both a is equal to 0 and a is not equal to 0, it is true for all a. Okay, so kind of broad picture here. Binomial Theorem 2 is the one that you can always go to if you want. But Binomial Theorem 1 is a little bit cleaner to prove since you don't have to mess with the a and the b. It's just a bit of personal choice of how you want to go about proving it. Okay, so let's look at an example. Find the coefficient of x to the 18th in this expansion here. So there's a few ways you can go about it, so let's present one. So by Binomial Theorem version 2, I have that this expression here is equal to this finite sum. So explicitly, I get 12 choose I get the term that's here, so x squared to the 12 minus I, and I get that minus 2x to the I. So this can be further simplified just by doing some algebra. So explicitly here, this minus 2 to the I can pull out front, and that will give me a remainder here of x to the I. So explicitly, I get a minus 2 to the I times an x to the I. So here, the minus 2 to the I part I pulled up front, and here, the x to the 2 to the 12 minus I. Well, this term is simply equal to x to the 24 minus 2i. And then when I multiply this thing times my x to the I simply get this this x to the 24 minus I term. Okay, so that's what's happening there in that simplification. So now I can ask the question, for what I does this term here equal x to the 18? If I know the value of I such that these two terms are equal, then the coefficient of the x to the 18th power will simply be this coefficient here whenever I plug in the value for I. So here, to solve this for I, I'd simply note that this is exactly when 24 minus I is equal to 18, or when I is equal to 6. Thus, the coefficient of x to the 18 is plug I is equal to 6 into here. So minus 2 to the 6, 12 choose 6. Or, if I work this out, minus 2 to the 6th is just 64. Pretty straightforward computation. 12 choose 6, that's 12 factorial divided by 6 factorial times 6 factorial. And here you can do whatever kind of simplifications you want to do to evaluate that. But here it's just 59,136. So now you can kind of see that binomial theorem lets me very quickly compute certain values like this. And there's actually quite a few connections between binomial theorem, the coefficients of the binomial theorem, the normal distribution, and various things you can do with counting. Explicitly, in some cases, you can turn a very particular type of counting problem into a problem of finding a particular binomial coefficient of a particular binomial expression. So yeah, kind of staying on that same topic, let's look at another example. Prove for all non-negative integers n that the sum of the binomial coefficients of this form is equal to 2 to the n. So how could I prove this? Well, a priori, I could use induction, right? I could prove that for n is equal to 1 or 0, that this is true. Then I could show via an inductive argument that it has to be true for all values of n, but that's not necessarily the nicest way to do it. Induction is pretty straightforward, but it's a fair bit of work to write out, and we've already actually done the hard work for this in the proof of the Binomial Theorem 1. So instead of using induction to do this, let's use the binomial theorem to do this. So explicitly, we know a plus b to the n is equal to this sum here for all a and b in the real numbers. So I can notice that this sum here looks very similar to this sum, with the caveat that a and b aren't in the sum up here. So how can I get rid of a and b? Well, a and b are any real numbers. Why don't I just let them both be equal to 1? Well, in that case, I get 2 to the n is equal to 1 plus 1 to the n, right? That's pretty straightforward on this side. And 1 plus 1 to the n, via this expression here, where a and b are both equal to 1, is simply equal to this expression here. Now, 1 to the n minus m and 1 to the m, both of those are equal to 1, so that's simply equal to the sum of the binomial coefficients. And we are done. So a good exercise to keep up your induction game would be to try proving this via induction. Essentially, you're repeating the argument that we did in Binomial Theorem 1 in a very particular case where x is equal to 1. So we will come back to this in the next lecture after Canada Day when we talk about Claim 33, but this example here is applicable to a particular counting problem that we'll introduce next lecture. Okay, so that's what we have for now. I want you to read pages 74 and 75. It's essentially the proof of the binomial theorem, so you don't technically have to read it if you want to try to avoid doing assigned reading and save some time, especially since you have your Math 119 midterm coming up and your assignment due relatively shortly. So yeah, and beyond that, we have a meme. So here, plugging into your calculator and choose m, using the formula for computing the factorials in your head. So here, if m and k are particularly nice, you might be able to compute this in your head. Expanding and computing the coefficient of the power of x. So here, explicitly, if I have x plus 1 to the n, this n choose k will be the coefficient of x to the k. Or you could write down the n rows of Pascal's triangle to find the kth element. So just write that out and do it. Or finally, making your own Galton board with n rows to experimentally obtain values for the binomial coefficients. So this is leading into the connection between all of this stuff and the normal distribution. But basically, this board is a board with a bunch of pegs. So to go into way too much detail of explaining the meme, I have a little channel where coins or dots or whatever can go down. And I have some pegs. So in the first row, I have 1 peg. And in the next row, I have 2 pegs. In the row after that, I have 3 pegs, and etc. So here, if I wanted to experimentally compute the coefficient of these binomial expansions, I can build this setup where I have these little containers at the bottom. So here I have these 4 little containers. This would be the coefficient for x to the 0, x to the first, x to the second, and x to the third. And it turns out that if you drop in 2 to the n, so in this case, 2 to the third coins into this, and repeatedly do this experiment, the average of the number of coins that end up landing in these little sections will be exactly the binomial coefficients. So here, the binomial coefficients for these two is 1, and the binomial coefficients for the two in the middle is 3. So on average, if you did that experiment, you would end up with this expression here. It's not necessarily the best way to do it, but that's kind of what this last bit is hinting at. We may talk about this later on when we start discussing probability, but that's kind of what's going on there. Okay, so have a wonderful long weekend and definitely enjoy the well-deserved break. I will see you next week.